It is the morning of October 14, 1943, a Thursday, and 291 B-17 Flying Fortresses are climbing into the cold air over East Anglia and turning east toward Germany. Their target is a small Bavarian city of 50,000 people named Schweinfurt, 400 miles deep inside the Reich, and the men flying toward it have been told that the factories clustered in that city are one of the most important targets in all of Germany. Not the aircraft plants, not the oil refineries, not the tank works, the ball-bearing factories. The 5 plants at Schweinfurt produced something close to half of all the ball bearings in Nazi Germany, and the planners of the combined bomber offensive had become convinced that the ball bearing was the secret weak point of the entire German war machine, the single small component on which everything else depended. Destroy the ball bearings, the theory went, and the tanks and the aircraft and the engines and the guns would all grind to a halt, because every one of them was full of ball bearings, and without ball bearings, nothing that spun could spin. By the end of that day, 60 of those 291 bombers would not come home. 600 American airmen would be dead, captured, or missing. The Americans would call it Black Thursday, and it would be one of the costliest single days in the history of the United States Army Air Forces, a catastrophe so severe that it would halt the deep daylight bombing of Germany until a long-range escort fighter could be found to protect the bombers. And here is the strange thing, the thing that sits at the center of this story, like a riddle. The men who flew to Schweinfurt to destroy Germany's ball bearings, in the belief that ball bearings were the indispensable heart of modern war, were flying in aircraft and would soon be escorted by a fighter whose own engines did not run on ball bearings at all. The most important bearings in the American war machine, the bearings deep inside the engines that powered the bombers and the fighters, the most heavily loaded and most critical bearings of all, were not ball bearings. They were something else entirely, something the popular history has almost completely forgotten. And understanding what they were and how they worked is the key to a question that sounds impossible, but is not. How do you build a fighter plane whose engine spins 3,000 times a minute under tons of crushing load without a single ball bearing anywhere near its crankshaft? The answer is one of the quiet triumphs of American engineering, and it begins with a riddle about the nature of the ball bearing itself. To understand why the Allies sent 600 men to die over Schweinfurt, you have to understand the near-religious faith that the modern industrial world placed in the ball bearing. The ball bearing is one of those inventions so fundamental, so ubiquitous, and so hidden that almost nobody thinks about it. And yet by the middle of the 20th century, virtually every machine that contained a rotating shaft contained ball bearings. The German aviation industry alone consumed something on the order of 2.5 million bearings every month. Aircraft engines, tank transmissions, gun turrets, superchargers, propeller hubs, electric motors, machine tools, the very lathes and grinders that made all the other weapons, all of them spun on ball bearings or their close cousins, roller bearings. The ball bearing had become the universal joint of the industrial civilization, the small round thing that allowed everything else to turn. This ubiquity was exactly what made it such a tempting target. The Allied planners reasoned, with a logic that seemed irrefutable, that if every machine needed ball bearings, and if German ball bearing production was concentrated in a handful of factories in one small city, then destroying those factories would create a bottleneck that would strangle the entire German war economy. It was the theory of the choke point, the single critical node whose destruction collapses the whole network. And the ball bearing seemed like the perfect choke point, because it was everywhere, because it was essential, and because it was concentrated. Albert Speer, the German armaments minister, would later admit that he had been genuinely frightened by the Schweinfurt raids, that he had warned that sustained attacks on the ball-bearing industry could cripple German armament production within months. The faith in the ball bearing as the indispensable component was not foolish. It was shared by the men who ran the German war economy as much as by the men who tried to destroy it. Everyone believed in the ball bearing, which makes it all the more remarkable that the engines of the aircraft fighting this very battle had, at their core, found a way to do without it. This is the paradox this story is built on. The entire strategic logic of the Schweinfurt raids rested on the premise that the ball bearing was irreplaceable, that no machine of war could function without it. And yet the single most important machine in the air battle over Schweinfurt, the piston-arrow engine, the Wright and the Pratt and Whitney radials in the bombers, the Allison and the Packard-built Merlin in the fighters, did not use ball bearings for its most critical, most heavily loaded function. The crankshaft of an American fighter engine, the spinning steel heart of the whole machine, the shaft that absorbed the colossal hammer blows of a dozen cylinders firing thousands of times a minute, did not ride on ball bearings. It rode on plain bearings, smooth curved shells of metal with no balls, no rollers, no moving parts at all. The resolution of the paradox is a piece of engineering physics so elegant that it seems almost like a trick. It turns out that for the specific, brutal job of supporting a crankshaft, the ball bearing is not the best solution at all. It is, in fact, a rather poor one. The best solution is the plain bearing, and the plain bearing works on a principle so counterintuitive that it took engineers decades to fully understand it. In a properly working plain bearing, the spinning shaft never actually touches the bearing at all. It floats, suspended on a microscopically thin film of pressurized oil, riding on a cushion of liquid that the shaft's own rotation creates and sustains. The crankshaft of a Merlin engine, turning 3,000 times a minute, carrying loads of tons, is held away from the metal of its bearings by a film of oil thinner than a human hair, and the metal never touches metal at all. This is the secret. This is how you build an engine without ball bearings. You float the crankshaft on oil. And the story of how American and British engineers perfected this, of the materials they developed and the manufacturing they mastered, is the story of how the Allies built the engines that won the air war without depending on the very component they were trying to bomb out of existence. The popular history of the air war remembers Schweinfurt as a story of sacrifice and of the limits of strategic bombing, the costly raids that proved bombers could not survive deep over Germany without escort. It remembers the ball bearing as a kind of tragic obsession, the choke point that turned out not to be a choke point, because the Germans dispersed their production and drew on their stockpiles and kept their machines turning. What the popular history almost never mentions is the other half of the story, the engineering half. The fact that the bearings that mattered most in the Allies' own war machine were not ball bearings at all, and that the mastery of the plain bearing was one of the unsung industrial achievements that made the Allied air forces possible. This omission is understandable because the plain bearing is the least glamorous component imaginable. It is a curved sliver of metal, a shell, a shim. It has no moving parts. It does its work in the dark, deep inside the sealed crankcase of an engine, invisible and silent, floating a crankshaft on a film of oil. Nobody photographs it. No raid was ever flown to destroy it, because it could not be concentrated in a single city, because making it required not a specialized ball-bearing industry, but the ordinary metallurgical and machining skills that were spread across the entire American manufacturing economy. And that precisely was its strategic virtue. The plain bearing could not be bombed out of existence because it was not made in 5 factories in one city. It was made everywhere, by everyone, out of steel and bronze and silver and lead. The story of the plain bearing is the story of why the Allied engine industry had no Schweinfurt, no single vulnerable choke point, and it is a story told in the physics of oil films and the metallurgy of soft metals, the kind of deep engineering that the popular history skips, and that is, in the end, where the real understanding lives. To understand why the crankshaft does not use a ball bearing, You first have to understand what a ball bearing is and why it became so beloved. A ball bearing is a device for letting a shaft rotate with as little friction as possible. It consists of two concentric rings called races, an inner race that fits on the shaft and an outer race that fits in the housing, and between them a set of hardened steel balls held in a cage so they are evenly spaced. When the shaft turns, the balls roll between the two races, and rolling, as humanity discovered when it invented the wheel, is vastly easier than sliding. The genius of the ball bearing is that it replaces sliding friction with rolling friction, and rolling friction is tiny. A shaft on ball bearing spins almost freely, with very little resistance, very little heat, and very little wear, as long as the bearing is clean and properly loaded. This is why the ball bearing conquered the industrial world. For a shaft that needs to spin fast and freely with minimal friction, a shaft in an electric motor, a machine tool spindle, a supercharger impeller, a wheel, the ball bearing is close to ideal. It supports the shaft precisely, it lets it spin with almost no drag, and it requires only modest lubrication. The roller bearing, its cousin, replaces the balls with cylindrical rollers, spreading the load over a line of contact rather than a point, allowing it to carry heavier loads. Together, ball and roller bearings, the rolling element bearings, became the universal solution to the problem of the rotating shaft, and the industry that made them became one of the foundations of modern manufacturing. It was a genuinely superb technology, and the Allied planners were not wrong to see it as essential. They were only wrong about one thing. They assumed that because the ball bearing was the best solution for so many rotating shafts, it must be the best solution for all of them. And the crankshaft of a piston engine is the great exception, the place where the ball bearing fails and something else must take its place. Here is why the ball bearing, so perfect for so many things, is wrong for a crankshaft. And understanding this is the key to the whole story. The problem is the nature of the load. A ball bearing carries its load through the tiny points where the balls touch the races. Each ball contacts the inner race and the outer race at a single, microscopically small point, and all the force passing through the bearing is concentrated at those points. As long as the load is steady and moderate, this is fine. But a crankshaft does not deliver a steady, moderate load. It delivers a savage, pounding, cyclic load, a series of violent hammer blows. Every time a cylinder fires, the explosion drives the piston down with a force of tons, and that force slams through the connecting rod into the crankshaft and then into the bearing. A sharp, sudden impact, repeated for every cylinder, thousands of times every minute. In a V12 like the Merlin, turning 3,000 revolutions a minute, the bearings absorb tens of thousands of these hammer blows every minute, hour after hour. A ball bearing, asked to carry this load, would destroy itself. The concentrated point contacts where the balls meet the races would be pounded by each impact, and the metal at those points, subjected to that relentless hammering, would begin to fatigue and crack and spall, flaking apart under the cyclic stress. The hardened steel of the races would brinell, develop tiny dents at each ball position from the pounding, and once the smooth race was dented, the bearing would roughen and fail. There is a further problem. A crankshaft is a one-piece forging with the bearing journals in the middle of it, so any bearing on a crankshaft journal has to be split, made in two halves that clamp around the journal, because you cannot slide a one-piece bearing over the middle of a crankshaft. A split ball bearing is a weak and difficult thing with a break in each race that the balls must roll across, and a ball bearing big enough and strong enough to take the crankshaft's loads would have to be physically large, forcing the whole engine to be bigger and heavier to accommodate it. For all these reasons, the ball bearing is simply the wrong tool for the crankshaft. It cannot take the pounding, it cannot easily be split, and it would bloat the engine. The crankshaft needs a bearing that can absorb continuous savage cyclic loads spread over a broad area, that can be split easily into shells and that is compact. And that bearing is the plain bearing, which solves all three problems at once by means of a beautiful piece of physics. Now we come to the heart of it, the thing the popular history never explains, the physics that lets a crankshaft spin without ball bearings. A plain bearing is, at first glance, almost absurdly simple. It is just a smooth, curved shell of metal, wrapped most of the way around the crankshaft journal, with a small clearance between the bearing and the shaft, a few thousandths of an inch. There are no balls, no rollers, no moving parts. The shaft simply turns inside the smooth metal sleeve. And if that were all there was to it, the bearing would be a disaster because metal sliding directly on metal generates enormous friction and heat and would seize and weld itself solid in seconds. The plain bearing does not work by sliding metal on metal. It works by never letting the metal touch at all, and the thing that keeps them apart is oil. Here is the physics, and it is genuinely beautiful. Oil is pumped into the small clearance between the shaft and the bearing under pressure. As the shaft begins to turn, it does something remarkable. It drags a layer of oil around with it, because oil clings to the surface of the spinning shaft. And because the shaft sits slightly off-center in the bearing under load, resting a little closer to the bearing on the loaded side, the gap between the shaft and the bearing is wedge-shaped, narrowing on the side where the load presses. The spinning shaft drags oil into this narrowing wedge, and as the oil is forced into the ever smaller gap, its pressure rises enormously. The faster the shaft spins, the more oil it drags into the wedge, and the higher the pressure climbs, until the pressure of the oil film in the wedge is great enough to support the entire load on the bearing, to actually lift the shaft and hold it away from the metal. This is called hydrodynamic lubrication, and the effect is that the spinning shaft floats on a self-generated wedge of pressurized oil, riding on a film thinner than a human hair, never touching the bearing metal at all. The rotation creates the pressure, and the pressure carries the load. The shaft does not slide on the bearing. It hydroplanes on a film of oil that its own motion creates. This is why the plain bearing can take loads that would destroy a ball bearing. The load is not carried at tiny points of metal contact. It is carried over the entire broad area of the oil film, spread across the whole curved surface of the bearing, cushioned by a layer of liquid that absorbs the hammer blows of combustion like a shock absorber. The pounding cyclic load of the crankshaft, which would brunel and crack a ball bearing's races, is simply soaked up by the oil film, distributed over a large area and damped by the give of the liquid. The plain bearing turns the crankshaft's savage impacts into a steady pressure on a cushion of oil. It is, when you understand it, a far more elegant solution to the crankshaft problem than any rolling bearing could ever be. And it requires no specialized ball bearing industry to produce. It requires only a precisely made metal shell, the right soft metal on its surface, and a steady supply of oil under pressure. The oil film does most of the work, but it does not do all of it, and this is where the metallurgy becomes critical and where the real engineering challenge of the plain bearing lies. The oil film carries the load when the shaft is spinning at speed, but there are moments when the film fails, when metal does touch metal, and the bearing surface has to survive those moments. When the engine first starts, before the oil pressure has built up, the shaft rubs directly on the bearing. When the engine is shut down and the oil drains away, the shaft settles onto the bearing. Under extreme loads, the film can be momentarily squeezed thin enough that the high points of the metal touch. And throughout the engine's life, tiny particles of grit and metal debris circulate in the oil, particles that can score and gouge a bearing surface. The bearing metal has to be able to survive all of this, and the properties it needs are a remarkable and almost contradictory set. It has to be soft enough to be forgiving. When a hard particle of grit comes through with the oil, the bearing surface needs to be soft enough that the particle embeds itself into the bearing metal and buries itself harmlessly, rather than being dragged across the precious hardened steel of the crankshaft journal and scoring it. This property is called embeddability, and it is why bearing surfaces are made of soft metals. The surface also needs to be conformable, soft enough to deform slightly, and adjust to tiny misalignments between the shaft and the bearing, spreading the load evenly rather than concentrating it. And it needs to resist galling, the tendency of two metals in contact to weld themselves together, so that in those moments of metal-to-metal contact at startup, the bearing slides rather than seizing. But here is the contradiction. The bearing also has to be strong. It has to have the fatigue strength to survive the pounding cyclic loads through millions of cycles without cracking. And it has to retain that strength at the high temperatures inside a running engine. And it has to resist the corrosive acids that form in the oil as the engine runs. Soft enough to be forgiving, strong enough to endure. These two demands pull in opposite directions, and the entire history of bearing metallurgy is the history of trying to satisfy both at once. The earliest solution to this problem was a soft white metal called babbitt, an alloy mostly of tin with some antimony and copper, invented in the 19th century. Babbitt is wonderfully forgiving. It is soft. It embeds grit beautifully. It conforms. It resists galling. It is an almost perfect bearing surface in terms of softness. The old way of making a bearing was to pour molten babbitt into the bearing housing and then scrape and fit it by hand to the shaft. A slow, skilled craft process. And for low-speed, lightly loaded engines, babbitt was fine. But babbitt has a fatal weakness for a high-performance engine. It is soft all the way through, and being soft all the way through, it lacks fatigue strength. Under the heavy pounding loads of a powerful engine, a thick layer of babbitt would fatigue and crack and break up. The very softness that made it forgiving made it weak. The breakthrough, the innovation that made the modern high-performance plane bearing possible was the thin-shell precision bearing, and it changed everything. Instead of a thick layer of soft metal, the engineers made a bearing out of a strong steel backing shell, a curved piece of steel that provided all the structural strength and fatigue resistance, and then bonded to the inside of that steel shell only a very thin layer of the soft bearing metal, a layer sometimes only thousandths of an inch thick. The thin, soft layer provided the forgiving surface properties, the embeddability and conformability, while the steel backing carried the load and provided the fatigue strength. Because the soft layer was so thin, bonded firmly to the rigid steel behind it, it could not flex and fatigue the way a thick layer did. The thin shell gave you both things at once, the soft surface and the strong structure, by separating them into two layers. And crucially, the thin shell bearing could be mass-produced, stamped, and machined to precise dimensions as a finished part that simply dropped into the engine, eliminating the slow hand scraping of the old babbitt bearings. The precision thin shell bearing, pioneered in America by companies like the Cleveland Graphite Bronze Company with its thin wall steel-backed bearings, was the foundation on which the high-performance aero engine bearing was built. It made the bearing both strong and forgiving, and it made it manufacturable in the millions. The thin shell solved the structural problem, but the question of exactly what soft metal to put on its surface remained, and as engines grew more powerful through the late 1930s and into the war, the demands on that surface grew beyond what babbitt could meet. The Rolls-Royce Merlin, in its early forms, used a bearing surface of lead bronze, a copper-lead alloy bonded to a steel shell, which was stronger than babbitt and could take higher loads. But as the Merlin's power climbed, as it went from 1,000 horsepower to 1,500 and beyond, even lead bronze began to struggle, and the search was on for a bearing that could survive the loads of the most powerful versions of the engine. And it was in America, at Packard, which was building the Merlin under license to power the P-51 Mustang and other aircraft, that the definitive answer was perfected. The American bearing was built in layers of extraordinary sophistication. Onto the steel backing shell, the engineers electroplated a layer of silver, around 40,000ths of an inch of pure silver, because silver is an outstanding bearing material, strong and an excellent conductor of heat, able to carry away the heat of the bearing. But silver alone has poor surface properties, so over the silver they plated a very thin overlay, around 2,000ths of an inch, of lead, which gave the soft, forgiving, embeddable running surface that the silver lacked. Silver for strength and heat conduction, lead for the forgiving surface. But the lead had a problem of its own. The combustion of the fuel produced acids that found their way into the oil, and those acids corroded the lead overlay, eating it away. And the solution to that was the final, elegant touch, the addition of indium, a rare soft metal. The bearing surface was flashed with a thin layer of indium, which was then heat diffused into the lead, and the indium made the lead overlay resistant to the corrosive acids in the oil, dramatically extending the bearing's life. The result was the silver-lead indium bearing, a steel shell carrying silver carrying lead infused with indium, each layer doing a specific job. And it was one of the unsung material triumphs of the war. When Packard took over Merlin production, one of its key modifications was exactly this, changing the main crankshaft bearings to the silver-lead indium combination, which improved the running-in and the load-carrying ability of the surface. The crankshaft of the P-51's engine, the fighter that would soon escort the bombers to Schweinfurt and beyond, floated on a film of oil held by bearings of silver and lead and indium, not a ball bearing in sight. It is worth stopping to appreciate why this mattered at the level of grand strategy, because it transforms the plain bearing from an engineering curiosity into one of the quiet reasons the Allies could outproduce their enemies. The whole premise of the Schweinfurt raids was that bearing production was a choke point, a single, vulnerable node. And for the ball bearing, that was true, because making a precision ball bearing is genuinely difficult and specialized. It requires perfectly round, perfectly hardened, perfectly graded steel balls made to tolerances of millionths of an inch, and the machinery and expertise to make them was concentrated in a relatively small number of specialized plants. That concentration was what made the ball bearing industry bombable, what made Schweinfurt a target. The ball bearing was a choke point because it was hard to make and made in few places. The plain bearing was the opposite. It was, in a sense, deliberately unconcentrated. Making a thin shell plain bearing required precision, yes, but it required the ordinary skills of stamping steel and electroplating metals and machining shells to close tolerances, skills that were spread throughout the entire American manufacturing economy in hundreds of plants, not 5. There was no Schweinfurt for plain bearings, no single city whose destruction would halt their production, because they were made everywhere. The Allied aero engine, by running its most critical bearings on plain bearings rather than ball bearings, had reduced its dependence on the one component that was concentrated and vulnerable, and shifted that dependence onto a component that was dispersed and resilient. This was not a deliberate strategic choice, exactly. The engineers used plain bearings on crankshafts because plain bearings were the right tool for the crankshaft, for all the reasons of physics we have explored. But the strategic consequence was real and enormous. The Allies could not have their engine production strangled by a bearing choke point, because their engine's core bearings were not the bearings that could be choked. The very thing the Allies were trying to do to Germany at Schweinfurt, to find and destroy the bearing choke point, could not have been done to the Allied engine industry, because that industry had, without quite intending to, designed the choke point out. And what of Schweinfurt itself, the raid that opened this story? The brutal irony is that the raids largely failed to achieve their purpose, and for reasons that echo the whole theme of this story, the resilience and substitutability of industrial production. American wartime intelligence claimed that the first raid in August of 1943 had cut German bearing production by 34%, and that the October raid had cut it by 40%. These figures were encouraging, and they were wrong. Post-war analysis, when the Allies could examine the actual German records, found that German ball bearing production had dropped by only about 10%, and even that was quickly recovered. The choke point had not been choked. The reasons were several, and they are instructive. The Germans had large stockpiles of bearings, which cushioned the immediate impact. They had access to imported bearings from neutral Sweden, whose great bearing maker SKF continued to sell to Germany, and from Switzerland, despite Allied diplomatic pressure. They dispersed their bearing production out of Schweinfurt into many smaller and harder-to-find locations. So there would no longer be a single concentrated target. And in the spirit of this entire story, they looked for substitutes, redesigning equipment where they could use other kinds of bearings, including plain bearings, in place of the ball bearings under attack. Albert Speer, who had been so frightened by the raids, organized exactly the kind of dispersal and substitution and recovery that blunted their effect. The destruction of buildings, it turned out, was far easier than the destruction of an industry's ability to produce, because an industry could disperse, could substitute, could draw on stockpiles and imports, could adapt. The ball-bearing choke point, which had seemed so compelling on the planning maps, proved far more resilient than the planners had believed, and the terrible cost of Black Thursday bought far less than the Allies had hoped. But Schweinfurt did change the war, just not in the way its planners intended. The catastrophic losses of the deep daylight raids, Schweinfurt above all, proved beyond any argument that the unescorted heavy bomber could not survive over Germany. The B-17, for all its guns and its armor, was being slaughtered by German fighters the moment it flew beyond the range of its escorts, and the bomber offensive ground to a near halt after Black Thursday precisely because the losses were unsustainable. The lesson was written in the blood of 600 men over Schweinfurt, and the lesson was this: the bombers needed a fighter that could escort them all the way to the target and all the way home, a long-range escort fighter, and no such aircraft existed in adequate numbers in the autumn of 1943. And the aircraft that answered that need, the long-range escort fighter that finally made the deep penetration of Germany survivable, was the P-51 Mustang. With the Packard-built Merlin engine, with the drop tanks that extended its range, the Mustang could escort the bombers from England to Berlin and beyond, and its arrival in strength in early 1944 transformed the air war, allowing the bombing campaign to resume and to break the back of the Luftwaffe. There is a closing of the circle here that is almost too neat to be true. The Schweinfurt raids, flown to destroy Germany's ball bearings, proved the need for the escort fighter that became the P-51. And the P-51's engine, the Packard Merlin, ran its crankshaft not on ball bearings, but on the silver-lead indium plane bearings that were America's quiet bearing triumph. The plane that the ball-bearing disaster called into being was itself a plane whose engine had transcended the ball bearing. The Mustang that escorted the bombers to the ball-bearing factories did not need those factories' product where it mattered most, in the spinning heart of its engine. Honesty requires a clarification, because the title of this story is a deliberate provocation, and the truth is more precise and more interesting than the slogan. America did not build planes entirely without ball bearings. A complete aircraft is full of rolling element bearings. The wheels turn on tapered roller bearings. The supercharger impeller, spinning at tens of thousands of revolutions a minute, rides on bearings. The magnetos and the generators and the starter motors have ball bearings supporting their rotors. The propeller reduction gear at the front of the Merlin uses roller bearings, and the propeller shaft itself takes its thrust on a ball bearing. The variable pitch propeller blades pivot on large ball bearings. There are rolling element bearings throughout the aircraft, and the Allies, like everyone else, needed a robust bearing industry to supply them, which is one reason the loss of bearing supply would have hurt the Allies too, had it ever been seriously threatened. The precise truth, the defensible and remarkable truth, is this: the single most critical, most highly loaded, most failure-intolerant bearings in the entire aircraft, the bearings that supported the crankshaft and the connecting rods, the bearings on which the whole engine, and therefore the whole aircraft, depended, were not ball bearings. They were plain bearings, floating the crankshaft on a film of oil, and they did a job that no ball bearing could have done. And because they were plain bearings, the heart of the engine was free of the one component that the Allies believed and hoped was the great vulnerable choke point of industrial war. The slogan that America built planes without ball bearings is an overstatement, but the truth beneath it is not. America built the engines that powered its planes so that their beating hearts, their crankshafts, turned without a single ball bearing on a cushion of oil held by shells of silver and lead. That is the real and the more wonderful fact, and it is the answer to the question the title poses. Here is how you build a plane whose engine runs without ball bearings. You understand the physics of the oil film. You master the metallurgy of the soft, forgiving surface on the strong steel back, and you float the crankshaft on a wedge of pressurized oil that its own spinning creates. That is how. The lesson of this story reaches beyond bearings into the nature of industrial resilience and the difference between a choke point and a distributed strength. The Allied planners went to Schweinfurt looking for the choke point, the single vulnerable node whose destruction would collapse the enemy's war machine, and they paid a terrible price discovering that the ball bearing, for all its ubiquity, was not the choke point they imagined, because an industry can disperse and substitute and adapt in ways that a planning map does not show. The deeper lesson is in the contrast between the two kinds of bearing. The ball bearing was concentrated, specialized, hard to make, made in few places, and therefore vulnerable. The plain bearing was dispersed, made of ordinary skills, spread across the whole economy, and therefore resilient, no choke point at all. There is a principle here that engineers and strategists alike keep relearning. The most robust system is often not the one built around the single best component, but the one whose critical functions do not depend on any single concentrated, vulnerable thing. The engineers who chose plain bearings for the crankshaft did not choose them for strategic resilience. They chose them because the physics of the oil film made them the right tool for the crankshaft's brutal cyclic loads. But the strategic resilience came along with the engineering correctness, as it so often does, because good engineering tends to produce robustness as a byproduct. The plain bearing was the right answer to the crankshaft problem, and being the right answer, it also happened to be the answer that no enemy could bomb. That is how engineering and strategy intertwine, and it is why the humble plain bearing, the curved sliver of silver-plated steel floating a crankshaft on oil, deserves to be remembered as one of the quiet weapons of the war. In a war decided by what kept turning at the heart of every Allied fighter engine was a crankshaft that touched nothing at all. It spun 3,000 times a minute, absorbing tens of thousands of hammer blows a minute from the firing cylinders carrying loads of tons, and it did so without a single ball bearing because it was not resting on metal at all. It floated, suspended on a film of oil thinner than a hair, a film that its own rotation dragged into a wedge and pressurized until the oil itself lifted the shaft and held it clear of the bearing. Silver below, lead and indium on the surface, steel behind, and between the bearing and the spinning steel of the crankshaft. Nothing but a microscopic cushion of pressurized oil, doing the work that everyone believed only a ball bearing could do. The Allies sent 600 men to die over Schweinfurt in the belief that the ball bearing was the indispensable component, the choke point, on which the whole machinery of war depended. They were half right. The ball bearing was indispensable for 1,000 things, and it was concentrated, and it was vulnerable, and the dream of strangling Germany by destroying it was a reasonable dream. But it was the wrong dream, partly because an industry can disperse and substitute and survive, and partly because of a deeper truth the planners never grasped, which was that the most critical bearing in their own war machine was not a ball bearing at all. The beating heart of the engine, the crankshaft, had transcended the ball bearing decades before, by means of a piece of physics so elegant it still seems like a magic trick, the floating of a loaded shaft on a self-made film of oil. In a war fought between industrial systems, the system that understood the oil film, that mastered the metallurgy of silver and lead and indium on a thin steel shell, that built the beating heart of its engines around a bearing that could be made everywhere and bombed nowhere, was a system with no Schweinfurt of its own to lose. The P-51 Mustang that rose out of the Schweinfurt disaster, the escort fighter that finally made the deep raids survivable, carried in its Packard Merlin a crankshaft floating on American oil film bearings, free of the very component the bombers had died trying to destroy. America did not build its planes without ball bearings, but it built the engines that powered them so that the one bearing that mattered most, the one that could not be allowed to fail, did not need a single ball at all. It needed only oil and silver and the understanding of how a spinning shaft under the heaviest load can ride forever on a cushion of liquid and never touch the metal beneath it. That understanding was the weapon, and it was one the enemy could never find on a map, never mark for destruction, never bomb. It was everywhere, and it was nowhere, and it kept the engines turning all the way to Berlin. That was enough. In a war decided by what kept turning, the thing that turned was a crankshaft floating on oil, and that, in the end, was how America built its planes without ball bearings.